up, everybody? This is Tech G back with another video. And in this video, we're going to be talking about the challenges that are associated with machine learning. So let's get into it. All right. So you started diving into the world of machine learning, and everything seems kind of magical, I guess you can say. You feed a computer a bunch of data, and boom, it can detect spam, predict the weather, or recommend your next favorite movie. But here's the reality check. Machine learning is not magic. It's math, data, and a whole lot of problem solving. And like any powerful tool, it comes with its own set of challenges. And three of the most common and most important ones that you're going to come across are called overfitting, underfitting, and data bias. And these issues, they can make or break your machine learning model. In fact, even if you're using the fanciest algorithms and state-of-the-art hardware, your model will fall flat if you don't understand and manage these challenges. So with that being said, we're going to go ahead and talk about these challenges one by one. Now, before we dive into the problems, let's remind ourselves what machine learning models actually do. So imagine you're trying to teach a machine how to predict house prices. You give it a bunch of examples like square footage, the number of bedrooms, location, and what those houses sold for. The goal is for the model to find patterns and learn the relationship between features, also known as input, and prices, which are also known as output. But here's the kicker. The model doesn't really understand houses or money. It just crunches numbers and finds patterns. And sometimes it finds patterns too well, and other times it doesn't find any meaningful pattern at all. That's where overfitting and underfitting come into play. Exactly what is overfitting? So overfitting, this happens when your machine learning model learns the training data too well, like obsessively well. It memorizes every tiny detail, even the random noise or errors in the data. It becomes a straight A student on the training data, but completely bombs the tests when it comes to new or unseen data. So imagine this, you're studying for a history test by memorizing every single word from the textbook. Then on the test, the questions are phrased differently, and you have no clue what to do. That's overfitting in a nutshell. And here are some signs that your model is overfitting. If you have high accuracy on training data, if it has a terrible performance on test or validation data, or it's a very complex model with too many parameters or too deep a neural network. So here's a real life example to make all this make sense. So let's say you're building a model to identify spam emails. You train it on thousands of messages, but your data set includes a weird pattern. Some spam messages are always sent at 3 o'clock in the morning. So your model learns that if it's 3 a.m., then it must be spam. Now, what's the problem? In the real world, lots of legit emails are sent at 3 in the morning, but your model has been trained on noise and not real patterns. So here's how to avoid overfitting. So the first thing is you can use more data. So get a larger, more diverse data set, which can dilute the noise. You can apply what is called regularization. So techniques like L1 and L2 regularization, this helps prevent the model from going overboard. You can do what is called cross-validation. This is where you train your model on different subsets of the data to ensure generalization. Then there's early stopping. This is when you stop training when performance on validation data stops improving. Then you can prune the model where you can reduce the complexity, where you have fewer layers or features. All right, next let's talk about underfitting. So underfitting, this is the opposite of overfitting. This is when your model is too simple to learn the underlying patterns in the data. It's like trying to use a single crayon to draw a realistic portrait. No matter how hard you try, you just can't capture the details. And your model basically performs poorly on both training and test data because it hasn't learned enough. And here are some signs of underfitting. So if you have low accuracy on both training and testing data, or you have very simple models like linear models when relationships are non-linear, or your model cannot capture the trends or patterns. And here's a real life example of underfitting. So let's say you're trying to predict house prices again, but you build a model that only looks at square footage and ignores all other variables like location, the number of bathrooms, etc. The model might draw a straight line through the data when you actually need a curve to reflect market trends. That's underfitting. Basically, your model's just too basic to get the job done. So here's how you can fix underfitting. So you can use a more complex model. You can try decision trees, ensemble methods, or deep learning. You can add more relevant features where you can include other useful data like neighborhood crime rates, school ratings, etc. You can train the model longer. So sometimes underfitting happens when the model hasn't had enough time to learn. And you can reduce bias by making sure that your model isn't overly constrained by assumptions like linearity. Now let's try to make all of this make sense real quick. When it comes to underfitting, what you're going to get is a straight line that is trying to fit a curvy set of points, yet it misses the mark entirely. Now, if you want a good fit, this is when you have a smooth curve that flows nicely through the data. And when it comes to overfitting, you're going to get a crazy zigzag line that hits every point perfectly, even the weird outliers. Now, the one that you want is the middle one because that is the one that accurately represents the data the best. Now let's talk about balance. So at the heart of overfitting and underfitting is something called the bias variance trade-off. So basically high bias, this equals underfitting where the model is too simplistic. High variance, this equals overfitting where the model is too sensitive to noise. Now the goal is to find a sweet spot with low bias and low variance, which leads to good generalization. So think of it like a tightrope walk. You go too far in either direction and your model will topple. All right, so next let's talk about data bias. So exactly what is this? Well, data bias, this happens when the data used to train your machine learning model isn't representative of the real world, where it could be skewed, incomplete, discriminatory, or just simply outdated. This means your model will make predictions that are inaccurate, unfair, or even harmful. And bias in data, this can lead to bias in decisions. And when machine learning is used in areas like hiring, healthcare, or criminal justice, the consequences can be serious. And here are some types of data bias. The first one is called sampling bias. This is when your training data doesn't reflect the diversity of the actual population. So for example, if you train a facial recognition model on mostly white male faces, it will struggle to identify women and people of color. You have what's called a label bias. And this is when the labels used for training are flawed or subjective. So an example of this would be in hiring. Resumes from women might have been historically rated lower, which the model then learns as a pattern. Then we have what is called measurement bias. And this is when features are measured inaccurately or inconsistently. So an example of this will be using zip codes as a proxy for income that can be misleading and discriminatory. Then you have what is called confirmation bias. And this is when data confirms a preconceived notion or hypothesis and ignores contradictory evidence. An example of this will be only including data that supports your prediction that older people don't use smartphones when in fact many of them do. Now that leads us to our next question. Exactly why does data bias matter? Well, because machine learning does not have morals. It just mirrors the data that we give it. So if your data is biased, your AI will make biased decisions. It doesn't mean the algorithm is evil. It means the input is flawed. So always remember, when it comes to building machine models, you have a saying called garbage in and garbage out. Now let's go over some real world examples of bias in AI. Let's talk about Amazon's hiring tool. So Amazon, they built an AI to help with hiring, but it was trained on resumes that were submitted over 10 years ago, mostly from men. The AI then began penalizing resumes that included the word women, like women's chess club captain. Another example is facial recognition fails. So studies have shown that facial recognition systems have higher error rates for people of color, especially Black women. Now, why is this? Well, this is because the training data wasn't diverse enough. And another example would be predictive policing. So some law enforcement tools, they use crime data to predict where crimes might happen. But if the data reflects historical over-policing in certain neighborhoods, the AI then ends up reinforcing those patterns. So that leads us to how can you detect and mitigate bias? Well, the first thing you can do is you can audit your data. So you can ask questions like who's represented and who's missing. You can also diversify your training set where you can include a wide range of ages, races, genders, and other groups. You can test fairness metrics, so you can evaluate model outcomes across different demographic groups. You can involve domain experts like ethicists, sociologists, and community leaders where they can provide insights algorithms cannot. And most importantly, you can just be transparent so you can share your data sources and model assumptions. Now, exactly what should you take away from all of this? Well, machine learning isn't just about building cool models. It's about building reliable, fair, and useful ones. That means understanding that overfitting isn't a flex, it's a flaw. Underfitting means your model is basically guessing, and data bias is the hidden enemy of fairness and accuracy. So getting your model to work in the lab is one thing. Making it work in the real world where things are messy, diverse, and unpredictable, well, that's where the real skill lies. So let's go ahead and wrap all this up. So here's the deal. Building machine learning models is exciting, but it comes with big responsibility. Your models, they can influence people's lives, reinforce or break stereotypes, and shape decisions. So don't just aim for accuracy, Aim for awareness. Be curious about your data, question your model's assumptions, and think beyond the numbers. Because in the end, the smartest machine learning practitioners aren't just those who can code, they're the ones who care about what the code actually does. Now, with all that being said, let's do some check on learning. So, our first question is, what is the main characteristic of an overfitted machine learning model? Is it performs well on new and unseen data? It has a low training error but high validation error. It can capture patterns in the training data, or it has poor performance on both training and testing data. And the correct answer is it has a low training error, but a high validation error. So overfitting happens when a model learns the training data too well, including its noise and outliers, which leads to low training error, but poor generalization to new data. And this results in a high validation or test error. Next question. Which of the following best describes underfitting in a machine learning model? Is it the model has memorized the training data perfectly? Is it the model is too simple to capture the underlying patterns in the data? Is it the model has a complex architecture with too many parameters? Or is it the model is biased towards the test data? And the correct answer is the model is too simple to capture the underlying patterns in the data. So underfitting, this occurs when a model is too basic or rigid to learn the structure of the training data, which can lead to poor performance on both training and test data. It usually results from a model with insufficient complexity. And our final question is, data bias in machine learning can lead to what? Faster training times, improved model accuracy, fair and balanced predictions, or discrimination against certain groups or inaccurate predictions? And of course, the answer is discrimination against certain groups or inaccurate predictions. So data bias occurs when the training data does not fairly represent the real world scenario. This can cause models to make unfair or inaccurate predictions, especially for underrepresented groups or scenarios not present in the data.